The universe is vast beyond comprehension, stretching far beyond what our minds can truly grasp. To even begin to think about its scale is to confront a paradox. We live on a tiny, fragile planet orbiting an unremarkable star, yet that star is only a minuscule speck in an ever-expanding cosmic ocean. When considering the enormity of everything around us, it becomes almost absurd to imagine our place within it. Our everyday experience, grounded in meters, kilometers, or even thousands of kilometers, is utterly dwarfed by the dimensions of the cosmos. The Earth, with all its mountains, oceans, and cities, is barely a dot in the grand scale of the universe, a fragile sphere suspended in an immense void. Even our Sun, which dominates our sky and sustains all life on Earth, is but a medium-sized star, one of hundreds of billions in the Milky Way galaxy alone. The scale of the universe forces us to confront concepts that defy intuition. Light, traveling at 299,792 kilometers per second, takes over 8 minutes to reach Earth from the Sun. That's just our local star, unimaginably close compared to the nearest other stars or the edges of our galaxy. Every moment spent contemplating these distances can feel simultaneously insignificant and awe-inspiring. Our entire species, with all of its history, achievements, and struggles, exists on a planet so small and fleeting that, from a cosmic perspective, it is practically invisible. To help frame this, consider the simple act of looking up at the night sky. Every star we see is a sun in its own right, many of them far larger, hotter, or more luminous than our Sun. But the stars visible to the naked eye are just a tiny fraction of what actually exists. Most stars remain hidden, either too faint or too far away for our eyes to detect. Beyond those stars lie billions of galaxies, each containing billions of suns. The scale of everything is not merely large, it is staggering, overwhelming, and humbling. It is an expanse so vast that even traveling at the speed of light, the fastest possible speed in our current understanding of physics, it would take millions or even billions of years to traverse it. Yet understanding this scale is not only a scientific endeavor, it is a philosophical one. Realizing the minuteness of Earth and our place in the cosmic panorama can alter perspective on what truly matters, fostering humility while igniting curiosity. It is an invitation to explore, to measure, to question, and to seek understanding in a universe that is constantly growing and changing. The drama of cosmic scale lies not just in its size, but in the realization that what we perceive is only a fragment of the reality surrounding us. Every discovery, every image captured by telescopes, every calculation astronomers make, slowly unfolds more of this magnificent panorama, yet always leaves us yearning for a glimpse beyond. From the swirling clouds of the Orion Nebula to the distant reaches of the Hubble Ultra-Deep Field, humanity has only begun to scratch the surface of understanding how vast the universe truly is. Our curiosity is the tool that allows us to imagine the unimaginable, to quantify the unthinkable, and to grasp, at least partially, our own minuscule existence against the backdrop of infinity. Each step we take outward, each photon we detect from a star millions or billions of light years away, reinforces a simple truth. Earth is tiny, our Sun is a mere point in the cosmic ocean, and yet we possess the remarkable ability to comprehend, in some measure, the scale of it all. When we talk about the size of the universe, we have to make an important distinction between what the universe actually is and what we are able to see. This distinction is summed up in the idea of the observable universe. The observable universe does not mean the whole universe. Rather, it is the region of space from which light has had enough time to reach us since the beginning of cosmic time. Because the universe has a finite age, around 13.8 billion years, we can only see as far as light has traveled during that period. But here's the twist. Space itself has been expanding during that time, stretching distances in ways that defy everyday logic. This means the edge of the observable universe isn't 13.8 billion light-years away. It's much farther. Due to the relentless expansion of space, the boundary of what we can observe lies at about 46 billion light-years in every direction, creating a sphere centered on us. In other words, from our vantage point, the observable universe has a diameter of roughly 93 billion light-years. This sphere is not centered on us because Earth is special. It is centered on us simply because we are the observers. If you stood on another planet halfway across the galaxy, the observable universe would look the same size, but shifted around that new location. Every observer anywhere in the cosmos has their own observable universe, bound by the same laws of physics and light travel. That boundary, known as the cosmic horizon, represents the ultimate limit of what we can directly study. It doesn't mean nothing exists beyond that line. It only means we have no way of receiving information from beyond it, at least not yet. And this is where the enormity of the cosmos deepens. What lies beyond the observable horizon? The answer is almost certainly more universe. There's no reason to believe that the universe simply ends at that boundary. The expansion of space suggests that vast stretches of galaxies, stars, and perhaps even entire structures of unimaginable scale lie forever outside our reach. In fact, many cosmologists suspect the universe is infinite, extending without end far beyond what we will ever be able to measure. If that is the case, then the observable universe is just a tiny bubble in an endless ocean, a sliver of reality limited by the speed of light and the age of the cosmos. Yet even within this observable portion, the scale is almost incomprehensible. The galaxies we detect at the edge are so distant that their light has been stretched by cosmic expansion into faint whispers of what they once were. We are not seeing them as they are today, but as they looked billions of years ago, when the universe was still young. Some of those galaxies may not even exist anymore in their original form. Their stars may have burned out, collided, or evolved into completely different systems. Yet their ancient light continues to travel toward us, carrying messages from an era when Earth itself did not yet exist. This idea that we are always seeing the universe in the past is another humbling truth about the observable cosmos. The deeper we peer into space, the further back in time we are looking. To gaze across billions of light years is to peer across billions of years of history, back toward the dawn of creation itself. The farthest light we have detected comes from the cosmic microwave background, the afterglow of the Big Bang, a faint whisper from 13.8 billion years ago. That radiation is like a photograph of the universe when it was only about 380,000 years old, filled with dense plasma and not yet lit by the first stars. Beyond that point, the universe was opaque to light, shrouded in a cosmic fog we cannot see through. So the observable universe is both a window and a wall. It is a window because it allows us to glimpse the story of cosmic history, stretching from the birth of galaxies to the formation of stars, to the creation of planets, and ultimately to life itself. But it is also a wall because it sets a firm boundary around what can ever be studied with light. Beyond that wall, we can theorize, speculate, and imagine. But direct observation may forever be impossible. This limitation can be frustrating, but it also adds to the mystery and beauty of the cosmos. Knowing that there are realms of reality forever hidden from us is a reminder that the universe is not ours to fully conquer or understand, but rather to explore as far as the laws of physics allow. When we narrow our focus from the vastness of the observable universe to our own solar system, it might feel like we're suddenly dealing with something manageable. After all, the solar system is our cosmic neighborhood. The sun, the planets, their moons, asteroids, comets, and the scattered icy bodies beyond Pluto. But even here, scale quickly becomes overwhelming. Our solar system seems enormous when viewed from Earth. The distance between Earth and the Sun is about 150 million kilometers, and we call that one astronomical unit. That distance alone is difficult to comprehend. Yet, to reach Neptune, the outermost planet, you'd need to travel nearly 30 astronomical units. And beyond that lies the Kuiper Belt and the Oort cloud, a theoretical sphere of icy debris that could extend tens of thousands of astronomical units from the Sun. Already, just thinking about the boundary of our solar system reveals staggering distances. But here's the catch. Despite its size, our solar system is nothing more than a speck when compared to the stars that surround it. Our Sun, the center of everything we know, is just an average star, categorized as a yellow dwarf. It is neither the largest nor the smallest type of star, and certainly not the brightest in the galaxy. To our eyes, it dominates because of its proximity, yet compared to many stars out there, it is modest. Consider Betelgeuse, a red supergiant in the constellation Orion. If you replaced our Sun with Betelgeuse, its swollen outer layers would extend beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars entirely. Then there's Uy Scuti, one of the largest known stars. Its radius is more than 1,700 times greater than the Sun's. If it sat where the Sun is now, it would stretch well past Saturn. The sheer enormity of such stars makes our entire solar system look insignificant in comparison. Even more humbling is the fact that our solar system isn't located in some grand or central region of the Milky Way. It's tucked away in a spiral arm, orbiting quietly around the galactic center every 225 million years. We are not even close to being in the heart of galactic activity. We are in the outskirts of a spiral arm, in what could be considered the suburbs of the galaxy. Our neighborhood is sparse, relatively calm, and insignificant against the backdrop of the galaxy's bustling billions of stars. To put things into perspective, the nearest star to us, Proxima Centauri, lies more than 4 light-years away. That might not sound too far until you translate it into distance. 4 light-years means that even traveling at the speed of light, the fastest speed possible, it would take more than 4 years to reach Proxima Centauri. Using current space technology, it would take tens of thousands of years. This nearest neighbor is so far away that despite being the closest star beyond our Sun, it is invisible to the naked eye. Multiply that by the hundreds of billions of stars scattered throughout the galaxy, and suddenly, our solar system shrinks into utter obscurity. When comparing the solar system to nearby stars, we also confront the diversity of stellar systems themselves. While our Sun is orbited by 8 planets, many stars host planets of their own, some larger than Jupiter, others small and rocky like Earth, orbiting at distances that vary dramatically. In many cases, stars come in pairs or even triplets, forming binary or trinary systems. Against this backdrop, our solar system appears unremarkable, just one planetary system among countless others. Our solar system feels vast because it is all we've ever known. But compared to the stars that dot our galactic neighborhood, it is barely a point of light. When astronomers zoom out from planetary distances to stellar distances, the shift in scale is so dramatic that the solar system collapses into near invisibility. Our mighty Sun, around which every atom of human history has revolved, is nothing more than an ordinary star among hundreds of billions, an ember flickering quietly in the corner of a grand cosmic furnace. To grasp the enormity of the universe beyond our solar system, we need a unit of measurement that can handle truly unimaginable distances. Astronomers use the light year for this purpose. A light year is the distance that light travels in a single year, moving at approximately 209,792 kilometers per second. In 1 year, light covers nearly 9.46 trillion kilometers. That's so vast that even the distance from Earth to the Sun, about 150 million kilometers, fits into it almost 63,000 times. When we discuss interstellar or intergalactic distances, using kilometers or miles becomes meaningless. Light years give us a scale we can begin to comprehend, even if only in abstract terms. The nearest star beyond the Sun, Proxima Centauri, is over 4 light-years away. That means its light takes more than 4 years to reach us, traveling at the maximum speed allowed in the universe. When we look at its faint glow in the night sky, we are literally seeing it as it was 4 years ago. But most of the stars we see with the naked eye lie within a few hundred or a few thousand light years. Even so, these numbers are staggering. To travel a few hundred light years with current technology would take millions of years. As we extend our gaze to other galaxies, the numbers become truly mind-bending. The Andromeda Galaxy, our nearest major galactic neighbor, is roughly 2.5 million light-years away. Its light that reaches us today left that galaxy long before humans even existed. And when we observe galaxies in the Hubble ultra-deep field, some of them are more than 13 billion light-years away. That is a distance so immense that it stretches back almost to the beginning of the universe itself. Light years also help us understand the concept of looking back in time. Every object in the cosmos that emits light is effectively a time machine. When we see a star or galaxy, we are witnessing it as it was when the light first left it. Observing distant objects means peering across epochs, seeing stars in the process of formation, witnessing galaxies colliding, or even glimpsing structures that may no longer exist in their observed form. This intertwining of distance and time is unique to astronomy. The farther away an object is, the further back in history we are seeing it. Even more extreme are intergalactic distances within clusters and superclusters. Light from some of the farthest known galaxies in these enormous structures has traveled tens of billions of years to reach us. While the universe continues to expand, the light from these galaxies stretches and reddens, a phenomenon known as redshift. By measuring this redshift, astronomers can calculate distances across cosmic time and map the large-scale structure of the universe. Using light years allows us to frame these colossal scales in a comprehensible way. It transforms abstract, almost incomprehensible numbers into something tangible, a distance defined by the fastest thing in the universe, the speed of light. Even so, when we say that a galaxy is billions of light years away, we are dealing with distances so extreme that imagining them is nearly impossible. Earth, the solar system, even our galaxy, seem infinitesimal against this cosmic backdrop. Our galaxy, the Milky Way, is the cosmic home we inhabit, yet even describing its size stretches the limits of imagination. It is a barred spiral galaxy, roughly 100,000 light-years across, with a thickness of about 1,000 light-years in the central bulge. If we were to travel at the speed of light, it would take 100,000 years to go from one edge to the other, highlighting just how vast it is compared to our solar system. Our Sun, along with its planets, resides about 27,000 light-years from the galactic center, orbiting at an astonishing speed of approximately 828,000 kilometers per hour, completing a single orbit roughly every 225 million years. This orbiting motion places us in a relatively calm neighborhood in one of the spiral arms, far from the tumultuous activity near the central black hole. The Milky Way contains an estimated 100 to 400 billion stars, each with the potential for planets of their own. These stars range from small, dim red dwarfs to massive blue giants, each contributing to the galaxy's immense diversity. The density of stars varies depending on location. Near the galactic center, stars are packed closely together, their combined gravity influencing the motion of surrounding stars and gas clouds. In the outer arms, the stars are spread more sparsely, and these quieter regions are where our Sun resides. The galaxy is also permeated by clouds of gas and dust, forming regions of starbirth known as nebulae, and remnants of dead stars scattered across the spiral arms. Within this massive structure, there are also billions of planetary systems, many of which we have only begun to detect. Exoplanet discoveries over the past few decades suggest that planets are not rare. Rather, they are a common feature of stars, meaning the Milky Way likely hosts hundreds of billions of planets, some possibly harboring life. This adds an entirely new dimension to the scale of our galaxy. Not only is it immense in terms of stars and distance, but it is also potentially teeming with countless worlds. Despite its immensity, the Milky Way is just one galaxy among billions. Yet within it, every cosmic phenomenon imaginable occurs. Stars are born in dense molecular clouds, massive stars explode as supernovae, neutron stars and black holes bend space itself, and gravity weaves an invisible web that keeps the galaxy bound together. Observing the Milky Way from Earth, particularly from dark skies away from city lights, we can glimpse a hazy band of stars stretching across the night sky. That faint glow is the combined light of billions of stars, each one a distant sun, and each one a reminder of our tiny place in this grand, rotating structure. Beyond the vastness of the Milky Way lies an even more mind-boggling cosmic expanse, a neighborhood of galaxies that stretches across millions of light years. These galactic neighbors are not mere points of light. They are massive star systems in their own right, each containing billions or even trillions of stars, complex structures, and the potential for countless planetary systems. Among the most famous of these neighbors is the Andromeda Galaxy, also known as M31, which is our largest and closest spiral galaxy. Andromeda lies approximately 2.5 million light-years from the Milky Way, a distance that dwarfs even the most extreme distances within our own galaxy. To imagine traveling to Andromeda at the speed of light would take 2.5 million years, a time span so vast that it defies any human scale of experience. Andromeda is truly colossal. It is roughly 220,000 light-years in diameter, more than twice the width of the Milky Way, and it contains around 1 trillion stars, significantly outnumbering the Milky Way's 100 to 400 billion stars. Its sheer mass and size make it a dominant feature of our local cosmic neighborhood. Andromeda is also moving toward the Milky Way at a speed of roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies are expected to collide, merging in a slow cosmic dance that will create a new, massive elliptical galaxy. While such a collision sounds catastrophic, on the scale of individual stars, the vast distances between them make direct collisions rare. Instead, gravity will rearrange stellar orbits and reshape the structure of both galaxies in a process that unfolds over millions of years, a testament to the incredible scales of time and distance that govern galactic interactions. Andromeda is not alone. Surrounding the Milky Way and Andromeda are dozens of smaller satellite galaxies, dwarf galaxies that orbit their larger hosts like moons orbiting planets. Examples include the large and small Magellanic Clouds, visible from the southern hemisphere, which are gravitationally bound companions of the Milky Way. These dwarfs may contain only a few billion stars each, tiny in comparison to the Titanic spirals, yet they are integral to understanding galactic evolution. Over billions of years, these smaller galaxies may merge with their larger neighbors, delivering stars, gas, and dark matter, and shaping the future structure of their host galaxies. The scale of these galactic neighbors begins to illuminate just how small our solar system is, and even how minuscule our entire Milky Way appears when set against the broader cosmos. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and about 54 other smaller galaxies, spans more than 10 million light-years. Within this group, gravity binds the galaxies together, forming a coherent system that moves as a unit through space. Yet even the local group is just a tiny fragment of a larger structure. Beyond it lies the Virgo supercluster, a massive cluster of clusters, encompassing tens of thousands of galaxies spread across more than 110 million light-years. As we survey the galaxies beyond the Milky Way, the diversity is staggering. There are elliptical galaxies like M87 in the Virgo cluster, where trillions of stars are packed into a smooth, spheroidal shape. There are irregular galaxies, often chaotic and misshapen, possibly disrupted by past gravitational encounters. Spiral galaxies like Andromeda and the Milky Way dominate the visible universe, their elegant arms spinning gracefully around dense central bulges. Each of these galaxies, no matter how small or faint, contributes to the cosmic tapestry, a network of systems interacting through gravity and dark matter, creating a complex, dynamic universe on an unimaginable scale. Even our perception of distance is challenged when we consider these neighbors. Andromeda, close enough to appear as a faint smudge in binoculars, is separated from the Milky Way by a gap larger than the distance between our solar system and the outer edges of the galaxy, multiplied thousands of times over. Traveling from one edge of the Milky Way to Andromeda would be like crossing a vast ocean that stretches for millions of years at the speed of light. And yet, the universe does not stop there. Beyond the local group, there are countless other galaxy groups and clusters forming a cosmic web of extraordinary complexity. This network of galaxies, each with its billions of stars, planets, and potential for life, highlights just how incredibly vast the universe is. The observable universe contains roughly 2 trillion galaxies, a number so staggering that imagining each one individually is impossible. Each galaxy is a universe in miniature, a swirling collection of stars, planets, gas, and dust, moving in intricate patterns governed by gravity and the expansion of space. When we consider our galactic neighbors, we begin to understand that the Milky Way, enormous as it feels from within, is just a single participant in a cosmic neighborhood of unimaginable size and diversity. The distances between galaxies are so extreme that light itself, moving at the fastest speed possible, takes millions of years to travel even the short distances between members of the local group. Between more distant galaxies in the Virgo supercluster, light must journey tens of millions of years. Across the vast expanse of the observable universe, light may take billions of years to reach us. Every galaxy we see in a telescope is a glimpse into the past, and every faint smudge of light represents the accumulated brilliance of billions of stars, each potentially with its own planets, moons, and cosmic phenomena. Considering galactic neighbors forces a dramatic shift in perspective. The Milky Way, immense and magnificent from our point of view, is only a fraction of the structure of the cosmos. Our solar system is barely a dot even within our own galaxy, and our galaxy is a mere speck when set against its neighbors. Yet, this is precisely what makes the universe so humbling and awe-inspiring. The scale challenges our comprehension, stretching our imagination to the limits, reminding us that everything we know, the Earth, the Sun, our planets, even our galaxy, is part of a far larger, intricate, and interwoven cosmic structure. As we step back from individual galaxies and their immediate neighbors, the universe begins to reveal an even larger and more intricate pattern. Galaxies are not scattered randomly through space. They are organized into immense structures known as galaxy clusters. A galaxy cluster is a gravitationally bound collection of galaxies, ranging from a few dozen to thousands, all orbiting a common center of mass dominated by dark matter. These clusters are the building blocks of the large-scale structure of the universe, forming nodes in a vast cosmic web that stretches across hundreds of millions of light years. The nearest major cluster to us is the Virgo cluster, which lies about 55 million light years away. It contains over 1,500 galaxies, including ellipticals, spirals, and irregulars, all moving through a gravitational dance orchestrated over billions of years. Within clusters, galaxies can collide, merge, or gravitationally influence one another, sometimes triggering bursts of star formation or the growth of supermassive black holes at their centers. These interactions, although occurring on timescales far beyond human comprehension, shape the evolution of galaxies and, by extension, the cosmic environment in which we exist. Clusters themselves are not isolated. They are connected by filaments of dark matter and gas, forming massive superclusters. A supercluster is a grouping of clusters bound together, creating structures that span hundreds of millions of light years. One of the most well-studied superclusters is the Laniakea supercluster, which contains the Milky Way, along with roughly 100,000 other galaxies. Laniakea spans over 500 million light-years and has a mass equivalent to around 100 million billion suns. These vast conglomerations illustrate a scale that is difficult to fathom, where gravity operates over incomprehensible distances to organize matter into coherent, massive structures. Beyond these superclusters, even larger arrangements emerge, forming a cosmic web of filaments and voids. The filaments are the dense strands where clusters and superclusters congregate, while the voids are enormous regions of near-empty space, spanning hundreds of millions of light-years with very few galaxies. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, extends over 10 billion light-years, dwarfing even the largest superclusters. These enormous formations are the backbone of the universe, demonstrating that cosmic structure is hierarchical, organized on scales that are almost impossible for the human mind to imagine. Clusters of galaxies reveal more than just organization. They expose the hidden mass of the universe. Observations of galaxy clusters show that the visible matter, the stars, planets, and gas, accounts for only a fraction of the total mass. The rest is composed of dark matter, an invisible substance that exerts gravitational influence but does not emit or absorb light. Dark matter forms the scaffolding upon which galaxies and clusters are built. Without it, clusters would not hold together. Galaxies would drift apart into the void. Studying clusters provides critical evidence for dark matter and allows astronomers to map the distribution of this mysterious component on scales that encompass millions of light-years. Another fascinating aspect of galaxy clusters is the role they play in cosmic evolution. Clusters often contain hot, diffuse gas that emits X-rays, a signature of the intense gravitational interactions taking place. Galaxies falling into clusters can have their gas stripped away, slowing star formation and altering their morphology. In some cases, galaxies are torn apart entirely, their stars joining the intra-cluster medium. This dynamic environment illustrates that galaxies are not isolated islands, but part of an interconnected, ever-changing cosmic ecosystem. Superclusters, clusters, and filaments together form the largest structures known in the universe, providing a framework for understanding how matter is distributed across cosmic scales. The hierarchical nature of the cosmos, from stars to galaxies, galaxies to clusters, clusters to superclusters, mirrors fractal-like patterns, where similar organizational principles operate across vastly different scales. This hierarchical structure also reflects the history of the universe. Tiny fluctuations in the density of matter in the early universe, magnified by gravity over billions of years, gave rise to the intricate tapestry of cosmic structures we see today. When we contemplate galaxy clusters and superclusters, the scale of the universe becomes almost incomprehensible. Distances within a single cluster can be tens of millions of light-years, yet clusters themselves are mere nodes in a network spanning billions of light-years. The Milky Way, seemingly enormous from our perspective, is just one galaxy among hundreds of billions in its cluster, which in turn is part of a supercluster stretching across hundreds of millions of light-years. Our position in the cosmos is, in every sense, infinitesimal, yet our capacity to observe, measure, and understand these structures allows us to grasp their existence and scale. Zooming out even further, the universe reveals a pattern so vast and intricate that it resembles a colossal web woven across the cosmos. Astronomers call this the cosmic web, a vast network of filaments, nodes, and voids that forms the large-scale structure of everything we can observe. Unlike the relatively isolated stars of a galaxy or the clustered galaxies within a supercluster, the cosmic web represents the underlying organization of the universe itself. It is a network where galaxies, galaxy clusters, and superclusters are connected along dense, thread-like filaments, while enormous, nearly empty regions, known as voids, stretch for hundreds of millions of light-years between them. This large-scale structure is the ultimate manifestation of gravity shaping matter over cosmic time, and it gives us the clearest view of the universe's architecture on the grandest scales. The cosmic web is not just a theoretical construct. It is revealed through large-scale surveys of galaxies, mapping the positions and movements of millions of galaxies across the observable universe. These maps show that galaxies are not distributed randomly. Instead, they are concentrated along filaments, creating long, narrow chains that span tens to hundreds of millions of light-years. These filaments intersect at nodes, which are often sites of galaxy clusters and superclusters, forming the joints of the cosmic web. The spaces between these filaments, voids, are vast, almost completely empty, containing only a few isolated galaxies and extremely low-density gas. These voids can stretch for hundreds of millions of light-years, representing regions where the gravitational influence of surrounding matter has pulled most material outward toward denser areas. The formation of the cosmic web is a story that begins in the earliest moments of the universe. Tiny fluctuations in the density of matter, originating from quantum effects during the inflationary period, were magnified by gravity over billions of years. Denser regions attracted more matter, growing into filaments, clusters, and superclusters, while less dense regions became voids. Dark matter plays a crucial role in this process, providing the gravitational scaffolding that shapes the flow of ordinary matter. Without dark matter, the cosmic web as we know it would not exist. Galaxies and clusters would be far less organized, and the universe would appear much more homogeneous. Visualizations of the cosmic web reveal an intricate, almost organic structure. Filaments can be hundreds of millions of light-years long, yet only a fraction of that in width, like cosmic highways along which galaxies travel. Nodes where filaments intersect often host the largest clusters of galaxies, including massive elliptical galaxies and dense populations of smaller satellite galaxies. These intersections are gravitational wells, drawing in gas and galaxies and triggering the formation of new stars. Observing these regions allows astronomers to study the processes that govern galaxy evolution, star formation, and the behavior of dark matter. The voids between filaments are equally fascinating. They are not completely empty, but contain extremely diffuse gas and very few galaxies. Because matter is so sparse in these regions, galaxies that exist within voids evolve differently than those in filaments, often remaining small, isolated, and relatively unevolved. Studying voids helps scientists understand how environment influences the development of galaxies and offers clues about the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. The cosmic web also demonstrates the connectivity of the universe. Even though individual galaxies or clusters may seem isolated, they are part of an interconnected network stretching across billions of light-years. Light, gas, and even dark matter flow along these filaments, linking structures across unimaginable distances. Simulations of cosmic evolution, based on the laws of physics and observations from surveys such as the Sloan Digital Sky Survey, reproduce the web-like patterns with remarkable accuracy, confirming that the universe's large-scale structure is a natural outcome of gravity acting on the primordial distribution of matter. Beyond its scientific significance, the cosmic web is visually stunning and conceptually mind-bending. To picture it is to imagine a three-dimensional spiderweb extending across billions of light-years, with galaxies strung along threads of dark matter and immense voids forming the empty spaces between. Our Milky Way resides within one of these filaments, orbiting the center of mass of our local group and, by extension, the Laniakea supercluster. From our vantage point, we are inside a filament, peering outward toward countless other filaments and voids, each stretching far beyond what our eyes can see. The cosmic web also challenges our perception of emptiness and fullness in the universe. Galaxies are not uniformly sprinkled across space, but congregate where gravity has concentrated matter. The large voids, though vast and nearly empty, play an equally important role, shaping the flow of galaxies and the evolution of cosmic structures. This delicate balance between dense filaments and empty voids illustrates that the universe is not chaotic. It is structured on scales so enormous that even entire clusters of galaxies appear as mere points when viewed in the context of the cosmic web. Through the study of the cosmic web, we gain not just an understanding of scale, but of the dynamics that govern the universe. Galaxies move along filaments toward nodes, clusters merge and grow, and over billions of years, the cosmic landscape continues to evolve. It is a universe in motion, structured yet dynamic, immense yet ordered, revealing that our local neighborhood is part of a vast, interconnected cosmic system far beyond what we can fully observe. Even as we marvel at the structure of the observable universe, we must confront a humbling limitation. There are regions of the cosmos that may forever remain beyond our reach. The observable universe, vast as it is, extends only as far as light has traveled since the Big Bang, about 46 billion light-years in every direction. This limit is not a measure of the universe's true size, only of what we can see. Beyond this boundary lies the unobservable universe, a realm about which we can speculate but may never directly observe. These regions may contain galaxies, stars, planets, and structures as complex as, or more extreme, than those within our observational reach. Yet they are forever hidden by the finite speed of light and the relentless expansion of space. The idea that there are portions of the universe we cannot see is mind-bending. Imagine the universe as an infinite ocean, with the observable universe as a bubble floating at its center. Beyond that bubble, the waters stretch on endlessly, populated by unknown islands, currents, and phenomena that we can theorize about but will never measure. Some cosmologists propose that the universe is infinite, meaning the regions beyond our observation could mirror the observable universe or be radically different, with different densities, distributions of galaxies, or even distinct physical properties. The unobservable universe could contain trillions more galaxies than what we can detect, each with billions of stars, multiplying the already staggering numbers we use to describe cosmic scale. One of the reasons these regions may remain forever unobservable is the accelerating expansion of the universe, driven by dark energy. Galaxies beyond a certain distance are receding from us faster than the speed of light due to the expansion of space itself. While nothing can locally exceed light speed, space itself can expand without limit, effectively creating regions that light emitted from them can never reach us. As a result, vast portions of the universe are already beyond our cosmic horizon. Even if we wait billions of years, their light will never arrive, making them permanently inaccessible to observation. This creates a paradoxical universe. While it may be infinite and teeming with galaxies, only a finite portion is ever visible to us, and this observable patch is shrinking in relative terms as expansion accelerates. Speculating about the unobservable universe also raises profound philosophical and scientific questions. Could the laws of physics be different in regions we cannot see? Might there be galaxies with entirely unfamiliar chemical compositions, star formation processes, or cosmic phenomena we cannot even imagine? Some theories, including those related to inflation and the multiverse, suggest that these unobservable regions could vary in fundamental ways. Even the constants of nature, such as the strength of gravity, the charge of the electron, or the speed of light, might differ, leading to universes that are physically impossible for us to survive in or even comprehend. Our universe, as vast as it appears, could be a small segment of a far more complex and diverse cosmic reality. The concept of unobservable regions also challenges our notions of distance and time. When we look at galaxies near the edge of the observable universe, we are seeing them as they were billions of years ago. In the unobservable regions, events may have unfolded in parallel or on timelines entirely disconnected from ours, so the universe's history beyond our sight may be utterly unknowable. Galaxies could have formed, evolved, collided, or even disappeared in ways that we cannot detect.
The sheer scale and complexity of these hidden realms expand the mind's capacity for imagination, forcing us to recognize that the universe is far more extensive and mysterious than any measurement or observation can capture.
This perspective also highlights the limitations inherent in human observation. No matter how advanced our telescopes or how sensitive our instruments, we are constrained by the laws of physics and the age of the universe. Even light, the fastest messenger in the cosmos, cannot bridge certain distances if the space between us is expanding too rapidly. This means that, in some sense, the universe is only partially knowable. Our understanding is limited not by lack of curiosity or ingenuity, but by fundamental cosmic constraints. The unobservable universe is a reminder that the cosmos holds secrets that may be forever beyond our grasp, and that the true scale of reality may be far grander than we can ever perceive. Yet contemplating these invisible regions is not purely an exercise in futility. It is a profound invitation to explore, model, and imagine. Scientists use theoretical physics, cosmology, and simulations to extrapolate the structure and behavior of unobservable space based on the principles we can study. These speculations inform our understanding of the universe's formation, the distribution of matter, and the ultimate fate of cosmic structures. Even though we may never see beyond the observable boundary, theorizing about what lies there expands the horizon of human thought, pushing our imagination to confront infinity itself. One of the most profound revelations of modern cosmology is that the universe is not static. Far from being a fixed, unchanging backdrop for cosmic events, space itself is stretching, carrying galaxies away from one another in a slow but relentless expansion. This concept, known as the expanding universe, was first hinted at through observations in the early 20th century. In 1929, Edwin Hubble, examining the light from distant galaxies, discovered a remarkable trend. Almost every galaxy appeared to be moving away from us, and the farther away it was, the faster it seemed to recede. This relationship, now called Hubble's law, was the first concrete evidence that the universe is expanding, a discovery that fundamentally altered humanity's understanding of cosmic scale and history. The expansion of the universe is not like an explosion of matter into empty space. Rather, it is space itself that is stretching. Imagine the surface of a balloon with dots drawn on it. As the balloon inflates, the dots move away from each other, not because they are traveling across the surface, but because the surface itself is expanding. In the cosmos, galaxies are akin to those dots. They are not moving through pre-existing space in the conventional sense. Instead, the fabric of space between them is growing, stretching the distances on scales that are incomprehensible in human terms. This distinction is crucial. The galaxies are not fleeing through space like projectiles. They are being carried apart by the expansion of space itself. One of the most striking implications of this expansion is that it affects our perception of distance and time. Light emitted by distant galaxies is stretched along with space, a phenomenon known as cosmological redshift. The wavelength of light grows longer as space expands, shifting it toward the red end of the spectrum. By measuring this redshift, astronomers can determine how fast a galaxy is receding, and from there, estimate its distance. This effect also means that the farther we look into space, the faster galaxies appear to recede from us. Beyond a certain distance, galaxies move away so rapidly that their light may never reach us, effectively placing them beyond our observable universe. This expansion defines a cosmic horizon, a limit beyond which events are forever hidden, and it highlights the dynamic, ever-changing nature of the cosmos. The expansion of the universe also provides critical insight into its size. If space has been stretching for 13.8 billion years, and the rate of expansion has been accelerating due to dark energy, the current size of the observable universe is about 93 billion light-years in diameter. However, this is just the portion we can see. The universe itself may be far larger, potentially infinite,
stretching beyond the limits of observation. Its growth is not uniform either. On smaller scales, gravity dominates, holding galaxies and clusters together. But on the grandest scales, expansion dominates, pushing galaxy clusters apart and shaping the large-scale structure of the cosmic web. This duality, local stability versus cosmic expansion, creates a complex, layered understanding of scale and motion.
Dark energy, the mysterious force accelerating cosmic expansion, plays a central role in shaping the universe's ultimate fate. Discovered in the late 1990s through observations of distant supernovae, dark energy counteracts gravity on cosmic scales, causing the universe to expand at an ever-increasing rate. This acceleration means that galaxies currently within our observable universe will eventually drift beyond our detection. Billions of years from now, future civilizations, if they exist, may look back at the cosmos and see only the Milky Way and its immediate neighbors, with the vast majority of galaxies already receding beyond the cosmic horizon. In essence, the expansion of the universe continually rewrites the boundaries of what can be observed, ensuring that our view of the cosmos is both limited and temporary. The expanding universe also challenges our intuition about distance. Because space itself is stretching, two galaxies separated by tens of millions of light years are moving apart, not because they are traveling, but because the metric of space, the very distance between points, is changing. This distinction is important when considering extreme distances. Even if a galaxy's light is emitted toward us, if the expansion between us is too great, that light may never arrive. This creates a universe in which some regions are effectively unreachable, no matter how fast we could theoretically travel. The expansion is built into the fabric of reality, making certain regions permanently beyond reach and altering our understanding of cosmic connectivity. Observing the expanding universe also allows us to peer back in time. The farther a galaxy is, the longer its light has traveled to reach us, and the more we can see of the universe's past. In this way, expansion acts as a cosmic clock, revealing the history of the cosmos. Galaxies seen at extreme distances appear as they were billions of years ago, often during the universe's formative epochs. This time travel effect means that studying distant galaxies is equivalent to exploring the universe's evolutionary history, watching stars form, galaxies collide, and cosmic structures grow along the filaments of the cosmic web. Expansion thus connects the scale of space with the scale of time, adding a profound layer of complexity to our understanding of the universe. The expanding universe also reshapes our conception of cosmology itself. It suggests that the universe had a beginning, the Big Bang, a singular event in which space and time emerged, rapidly inflating and setting the stage for the cosmic web, galaxy clusters, and superclusters. Yet even as we study this expansion, we confront the possibility that what lies beyond the observable universe may have entirely different conditions, perhaps unaffected by the processes we can measure. Expansion implies that the universe is dynamic, alive with motion on scales that dwarf even the grandest galaxies, and that its boundaries, if they exist at all, are unreachable and possibly infinite. The implications of expansion extend to the future. If current models hold, the universe may continue to accelerate, galaxies drifting ever farther apart, stars exhausting their fuel, and clusters gradually dispersing. In this cosmic isolation, the night sky will grow emptier over trillions of years, leaving observers only with their local galactic group as the visible universe. This stark vision underscores both the grandeur and the impermanence of cosmic structures. Expansion is a force that not only defines scale, but also shapes destiny, ensuring that the universe we see today is just a transient snapshot of a far larger, ever-changing reality. Even as the universe expands, there exists a fundamental limit to what we can observe, a boundary known as the cosmic horizon. This horizon represents the farthest distance from which light has had time to reach us since the universe began. Essentially, it is the edge of the observable universe, the outermost boundary beyond which events are forever hidden.
While it might sound like a physical wall or a distinct line in space, the cosmic horizon is not a tangible object. It is a limit defined by time, light, and the speed at which the universe has been expanding. Everything beyond this horizon exists, but we cannot see it, and likely never will, because the light emitted from those regions has not had sufficient time to reach us, and in some cases may never reach us due to the acceleration of cosmic expansion.
The concept of the cosmic horizon can be understood through the interplay of distance, light, and time. Light travels at a finite speed, roughly 192 kilometers per second, which means that observing distant objects is always observing the past. The farther away an object lies, the longer its light takes to reach us. The universe is about 13.8 billion years old. So, in principle, one might assume we could see out to 13.8 billion light-years. However, because space itself is stretching as light travels, the distance to the farthest regions is much greater, approximately 46 billion light-years. This discrepancy arises because while light moves toward us, the fabric of space expands, effectively increasing the distance over time. The cosmic horizon therefore marks the maximum observable distance at any given epoch, taking into account the universe's expansion and the finite speed of light. The cosmic horizon is not static. As the universe ages, light from increasingly distant regions reaches us, slowly pushing the observable boundary outward. However, the accelerating expansion caused by dark energy introduces a profound limitation. Galaxies beyond a certain distance are receding faster than the speed of light due to the stretching of space. While this does not violate relativity, because relativity forbids objects moving through space faster than light, not space itself from expanding, it does mean that light emitted by these distant galaxies will never reach us. Consequently, a significant portion of the universe is permanently beyond our view, creating an observable universe that is only a fraction of the entire cosmos. The cosmic horizon also has deep implications for cosmology and our understanding of the universe's structure. Every observation we make is necessarily constrained to this horizon. When astronomers map the large-scale distribution of galaxies, filaments, and voids, they are working within the limits defined by the light that has reached Earth. Beyond the horizon, the universe could continue indefinitely, or it could contain variations in structure, density, or even physical laws. This unknown region challenges the notion that our observable universe is representative of the whole, forcing cosmologists to rely on theoretical models and simulations to infer what might exist in the unseen expanse. Importantly, the cosmic horizon is tied to the concept of causality. Because no signal or information can travel faster than light, events beyond the horizon cannot influence us. Galaxies, supernovae, or even entire civilizations beyond this boundary are fundamentally disconnected from our observable reality. Their existence may be entirely real, but in terms of interaction, observation, or measurement, they are unreachable. This gives the universe an intrinsic limit to knowability, a boundary not imposed by technology, but by the fundamental laws of physics. The cosmic horizon is thus a reminder of both the scale and the limitations inherent in our understanding. The horizon also affects how we interpret cosmic history. Light from the most distant galaxies we can see has traveled for billions of years, arriving from epochs when the universe was young and dramatically different from today. By observing these distant sources, we look back in time, seeing the universe in its formative stages. Yet, even this time-traveling view has a limit. Beyond the cosmic horizon, we cannot witness the early universe directly. There is simply no light from those regions that has reached us yet. This means that while we can reconstruct much of cosmic history, there are entire stretches of the universe's past that remain inaccessible, adding a layer of mystery to the ultimate scale of everything. The cosmic horizon is intimately connected to the concept of the Hubble radius, the distance at which the recession velocity of objects due to cosmic expansion equals the speed of light. Objects near this distance are effectively on the edge of the observable universe. Interestingly, the horizon does not coincide with a fixed point in space. It moves outward over time as light from more distant regions reaches us. Yet, the expansion ensures that some regions will always remain beyond this boundary, locked away from observation. This dynamic illustrates that the universe is both expanding and forever partially hidden, creating a profound tension between the observable and the unobservable. Moreover, the cosmic horizon provides perspective on the relative scale of everything we see. Galaxies, clusters, and superclusters within our horizon may seem staggeringly vast, but they are merely small islands within the far greater, unobservable universe. Even the largest structures we can detect, such as filaments stretching hundreds of millions of light years, are dwarfed by the potentially infinite expanse beyond the horizon. In this sense, the cosmic horizon represents the limits of human perception, a reminder that our cosmic map is incomplete and that the universe likely contains complexities and scales that we cannot even imagine. In essence, the cosmic horizon is a frontier, a boundary set by the interplay of light, time, and space itself. It defines the observable universe, limits our knowledge, and simultaneously inspires the imagination. It challenges us to confront the universe's immensity while recognizing that our understanding is inherently partial. As we develop more advanced telescopes and detection methods, we can push the horizon outward, capturing light from ever more distant objects. But the fundamental boundary imposed by the speed of light and cosmic expansion will always remain. The universe beyond this horizon may be infinite, teeming with galaxies, stars, and phenomena as complex and varied as those we can see, or it may hold surprises we cannot yet conceive. One of the most profound and mind-bending aspects of the universe is the intrinsic connection between time and space, a principle that becomes apparent the farther we look into the cosmos. When we observe distant objects, we are not seeing them as they are now. We are seeing them as they were when their light first began its journey toward us. Because light travels at a finite speed, every photon reaching our telescopes has traversed vast distances over years, centuries, or even billions of years. This creates a natural time machine, allowing us to witness the past and observe the universe at different epochs in its evolution. Looking deep into space is therefore equivalent to looking back in time, and this phenomenon transforms our understanding of scale into something profoundly temporal as well as spatial. For nearby stars, the effect is subtle but measurable. The light from Proxima Centauri, the closest star to our Sun outside of the solar system, takes approximately 4.24 years to reach us. Observing it is equivalent to seeing how it appeared just over 4 years ago, a minor temporal shift in human terms. Yet as we examine galaxies millions or even billions of light years away, the effect becomes staggering. The Hubble Space Telescope and other observatories routinely detect galaxies whose light has traveled over 13 billion years. This means we are observing these galaxies as they existed when the universe was less than 1 billion years old, a tiny fraction of its current 13.8 billion year lifespan. These observations allow us to study the formation of the first galaxies, the birth of stars, and the early distribution of matter in a universe still young and tumultuous. The connection between time and space introduces a scale that is not just immense in terms of distance, but also in terms of cosmic history. A galaxy observed at 10 billion light years away is not just far away in space. It is a glimpse into a time when the universe was dramatically different. The distribution of galaxies, their shape, and their composition reveal the processes shaping cosmic evolution. Early galaxies are often smaller, irregular, and richer in gas, in contrast to the more mature, structured galaxies we see nearby. Observing such ancient light allows astronomers to reconstruct the timeline of cosmic history, tracking the growth of structures from primordial density fluctuations to the vast cosmic web observed today. This temporal perspective also emphasizes the dynamic nature of the universe. When we observe distant galaxies, we are effectively looking at snapshots from a series of cosmic epochs, each revealing how matter, energy, and the forces of physics interact over immense periods. Supernovae exploding in distant galaxies, quasars emitting light from the cores of active galaxies, and gamma-ray bursts are all phenomena we witness as they occurred millions or billions of years ago. We are, in effect, watching cosmic history unfold in reverse, with each observation offering a glimpse into an epoch that no longer exists in the same form. This adds a profoundly mind-expanding layer to scale. The universe is vast not only in space but in time, and the farther we look, the deeper we peer into its history. The time-space connection also complicates our understanding of causality and interaction. Because light takes time to travel, events we see in distant galaxies occurred long before their photons reached us. A galaxy observed 10 billion light-years away may have evolved dramatically, merged with another galaxy, or even ceased to exist in its observed form, yet we see it frozen as it was billions of years ago. In this sense, our view of the universe is inherently partial and delayed, capturing only the light that has had time to traverse the cosmos, while the present state of distant regions remains unknowable until their light eventually arrives, if it ever does. The effect is magnified when considering the early universe. The cosmic microwave background, CMB, for example, is light emitted about 380,000 years after the Big Bang, over 13 billion years ago. Observing the CMB allows us to look at the universe at a stage when matter had cooled enough for photons to travel freely, revealing the primordial density fluctuations that would later grow into galaxies and clusters. In other words, looking at the CMB is equivalent to viewing the universe in its infancy, providing a blueprint of how structure formed over cosmic time. The time-space connection turns light itself into a historical record, encoding the story of the universe from its earliest moments to the present day. This principle also adds perspective to our understanding of distance. A galaxy 10 billion light-years away is not merely far away in a three-dimensional sense. It is also a window into a universe that was only 3 billion years old, with conditions, chemical abundances, and star formation rates drastically different from those observed locally. Space and time are inseparable in this context. The farther an object is, the earlier in cosmic history we see it. This union of distance and time forces a paradigm shift in thinking about scale. The universe is no longer just a spatial expanse. It is a temporal tapestry, where every observation is simultaneously an exploration of distance and a journey backward through time. The connection between time and space also emphasizes the relative nature of observation. Because the speed of light limits how fast information travels, no observer, regardless of location, can see the entirety of the universe at once. Each vantage point has its own observable horizon, meaning that the universe is experienced differently depending on where an observer resides. This relativity underscores the uniqueness of our cosmic perspective, while reinforcing the vastness and incompleteness of our view. Even if another civilization existed in a distant galaxy, their observable universe would differ from ours, containing regions we cannot see and missing parts of the cosmos we can. Ultimately, this intertwining of time and space enriches our comprehension of scale, making the universe incomprehensible in purely spatial terms alone. The vast distances between galaxies, the enormous clusters, and the intricate cosmic web are all rendered more profound when combined with the temporal dimension. Observing distant objects is a dual journey, across unimaginable spatial expanses and back through billions of years of cosmic evolution. Every telescope, every observation, every image captured of the farthest reaches of the cosmos is simultaneously a look across space and a look through time, reminding us that our universe is not static, but an evolving, historical, and interconnected system. As we contemplate the vastness of the observable universe, and even speculate about regions beyond our reach, An even more mind-expanding concept emerges: the possibility that our universe is not unique. The multiverse hypothesis suggests that what we call the universe might be just one of many universes, each with its own set of physical laws, constants, and structures. This concept is not merely science fiction. It has roots in theoretical physics and cosmology, arising from attempts to explain fine-tuning, cosmic inflation, and the underlying framework of reality itself. While empirical evidence for other universes remains elusive, the multiverse hypothesis offers a compelling lens through which to reconsider the scale of existence, pushing the limits of imagination far beyond even the unobservable regions of our own universe. One of the strongest theoretical motivations for the multiverse comes from cosmic inflation, the idea that the universe underwent a period of extremely rapid expansion in the first fractions of a second after the Big Bang. During this inflationary epoch, space expanded exponentially, smoothing out irregularities and setting initial conditions for the formation of matter and large-scale structures. Some inflationary models suggest that inflation might not have ended uniformly across all of space. In some regions, inflation could continue indefinitely, generating pocket universes where local physical conditions differ. In this view, our universe is merely one such pocket, forming a tiny island in a much larger, inflationary multiverse. Each pocket could have its own distinct constants of nature, resulting in universes with different rates of expansion, types of particles, or even dimensions. String theory, another leading candidate for a theory of everything, also provides a framework in which a multiverse might exist. According to string theory, fundamental particles are not zero-dimensional points, but tiny vibrating strings, and the way these strings vibrate determines the properties of particles and forces. The mathematics of string theory allows for a staggering number of possible configurations, on the order of 10^500 or more, each representing a different vacuum state of the universe. In essence, string theory predicts a landscape of possible universes, each with unique physical laws, constants, and structures. Our universe, with its specific values of gravity, electromagnetism, and other fundamental forces, might be just one of countless configurations in this cosmic landscape. The multiverse hypothesis also arises from considerations of quantum mechanics. In the many worlds interpretation, every quantum event with multiple possible outcomes leads to the branching of reality, creating parallel universes in which each outcome occurs. For example, when a radioactive atom decays, it might simultaneously decay and not decay, but in separate branches of the universe. Applied on cosmological scales, this idea suggests that an infinite number of universes might exist, encompassing every possible variation of reality. While this interpretation is highly speculative and difficult to test, it provides a theoretical underpinning for the idea that our universe is part of a far larger, possibly infinite, ensemble. The implications of a multiverse are staggering. If other universes exist, they could be entirely disconnected from ours, forever unobservable, and operating under different physical laws. Some might resemble our own universe, with galaxies, stars, and planets, while others could be radically different, perhaps containing no matter as we understand it, or operating in higher or lower dimensions. This shifts the concept of scale from unimaginable distances to unimaginable multiplicity, where our observable universe is but one instance in an almost infinite ensemble of realities. The multiverse hypothesis also provides a potential explanation for the fine-tuning problem. Our universe appears remarkably suited for life. The strength of gravity, the properties of atomic particles, and the expansion rate of the cosmos all fall within narrow ranges that allow for stars, planets, and ultimately observers like us. In a multiverse, this apparent fine-tuning is less mysterious. Given a vast number of universes with differing constants, it is inevitable that some universes will possess the right conditions for life. We happen to inhabit one of these rare universes simply because we could not exist in any of the others. In this sense, the multiverse offers a statistical explanation for why the universe appears so finely tuned without invoking design or coincidence. Yet the multiverse raises profound philosophical and scientific questions. If other universes are fundamentally unobservable, can we ever confirm their existence? How do we test hypotheses about regions that cannot interact with our own? These questions challenge the very nature of scientific inquiry, as traditional methods rely on observation and experimentation. Some theorists argue that indirect evidence, such as the statistical properties of the cosmic microwave background or the patterns of cosmic inflation, could provide hints of other universes. Others contend that the multiverse may remain forever in the realm of theoretical speculation, expanding our imagination but eluding empirical confirmation. From a conceptual standpoint, the multiverse dramatically redefines scale. Even if the observable universe stretches 93 billion light-years across, it may be infinitesimal in comparison to the totality of all universes. The sheer number of potential universes, each with its own vast dimensions and structures, introduces a layer of scale that dwarfs anything previously considered. Our Milky Way, our supercluster, and even the cosmic web within the observable universe could be tiny features in an unimaginably larger cosmic ensemble. Considering the multiverse shifts our perspective from thinking about the enormity of space and time to contemplating the enormity of existence itself, a scale that is both spatially vast and multiplicatively infinite. The multiverse also reshapes the human sense of significance and place in the cosmos. If countless other universes exist, each potentially hosting stars, planets, and perhaps life, the universe we call home is just one of countless cosmic islands. This perspective can be humbling, underscoring the infinitesimal fraction of reality that we experience directly. At the same time, it is exhilarating. It suggests that reality is far richer, more complex, and more varied than we could have ever imagined, and that our universe is part of an intricate and possibly infinite tapestry of existence. While the multiverse remains hypothetical, its implications are scientifically and philosophically profound. It challenges our notions of uniqueness, permanence, and the boundaries of knowledge. It encourages cosmologists to think beyond the observable universe and to consider structures, laws, and phenomena that may forever lie beyond direct detection. Even without empirical proof, the multiverse hypothesis transforms our understanding of scale, illustrating that the universe we perceive may be only a single bubble in an ocean of possibilities that stretches infinitely in all directions, both spatially and conceptually. To truly grasp the immensity of the universe, it helps to consider extreme distances on different cosmic scales. Even within our own galaxy, the distances between objects are staggering. But when we step outside the Milky Way, the scale becomes almost incomprehensible, and the differences between interstellar, intergalactic, and intersupercluster distances illustrate orders of magnitude that stretch the human imagination. Understanding these distances not only provides perspective on our place in the universe, but also highlights the practical challenges astronomers face in measuring, exploring, and conceptualizing cosmic structures. Within our own Milky Way galaxy, distances between stars are measured in light years, the distance that light travels in a single year, about 9.46 trillion kilometers, or nearly 5.88 trillion miles. Even our closest stellar neighbor, Proxima Centauri, is 4.24 light-years away, meaning that the light we see from it today left that star over 4 years ago. The vast emptiness between stars is a defining characteristic of galaxies. In some regions, stars can be separated by tens or even hundreds of light-years. While these distances seem immense in human terms, they are relatively small on a cosmic scale, and the stars themselves, though massive, are mere pinpricks of light compared to the enormous spaces separating them. Stepping beyond the Milky Way, we enter intergalactic space, where distances expand dramatically. The nearest major galaxy, Andromeda, lies approximately 2.537 million light-years from the Milky Way. Even traveling at the speed of light, it would take over 2 million years to reach it. Intergalactic distances are vast enough that entire galaxies appear as tiny points of light, even in telescopes. Unlike interstellar distances, where gravity dominates and binds stars into galaxies, intergalactic space is mostly empty, punctuated by individual galaxies, small groups, or galaxy clusters. The sheer emptiness of intergalactic space underscores the relative isolation of galaxies within the cosmic web, highlighting how even enormous structures like the Milky Way occupy a tiny fraction of the universe's volume. Beyond single galaxies and galaxy groups, the scale expands even further to inter-supercluster distances. Superclusters are vast conglomerates of galaxy clusters bound loosely by gravity, stretching hundreds of millions of light-years across. Our own Milky Way is part of the Laniakea supercluster, a structure roughly 520 million light-years in diameter, containing around 100,000 galaxies. Neighboring superclusters can lie hundreds of millions of light-years away, and the distances between them illustrate another jump in scale. These enormous separations make direct interaction between superclusters exceedingly rare. The forces binding galaxies within clusters are too weak to significantly influence galaxies across supercluster voids. When we speak of inter-supercluster distances, we are entering a domain where even light takes millions of years to traverse the emptiness, and entire galactic neighborhoods can drift apart while remaining gravitationally bound only on smaller scales. The orders of magnitude between these scales are staggering. Interstellar distances, like that between the Sun and Proxima Centauri, are measured in single-digit light-years. Intergalactic distances, such as the separation between the Milky Way and Andromeda, extend into millions of light-years. Inter-supercluster distances, meanwhile, span hundreds of millions of light-years, dwarfing even the largest individual galaxies. This exponential increase illustrates how rapidly cosmic scale grows as we move outward, transforming our intuitive sense of space into something almost incomprehensible. A single light-year, already enormous in human terms, becomes almost negligible when compared to the distance between clusters or superclusters, and yet it is the same unit used to describe both local and cosmic scale structures. These extreme distances also have practical consequences for astronomy. Observing distant galaxies and superclusters requires accounting for the time it takes light to travel, meaning that we are always looking back in time. Furthermore, intergalactic and inter-supercluster distances necessitate the use of indirect measurement techniques such as redshift, standard candles, and parallax for closer objects. Even the expansion of space itself must be considered, as the universe has grown while light traverses these vast expanses, stretching wavelengths and altering apparent distances. Understanding extreme distances is therefore not only a matter of imagination, but also a fundamental aspect of accurately mapping the universe and understanding its history. The scale of these distances also emphasizes the isolation and fragility of structures. Individual stars, though massive, are separated by immense voids. Galaxies float in intergalactic space, often separated by millions of light-years, while superclusters drift apart along the filaments of the cosmic web. These vast separations highlight that cosmic structures exist within a delicate balance of gravity, motion, and expansion. They also reveal the relative insignificance of any single object or structure within the larger universe, reinforcing the sense that the cosmos operates on scales far beyond human comprehension. To put these distances into perspective, consider the following. Traveling to Proxima Centauri at the speed of light takes just over 4 years. Traveling to Andromeda at the same speed would require over 2.5 million years. Traveling across a supercluster could take hundreds of millions of years. Each jump in scale magnifies the universe's size by orders of magnitude, demonstrating that even the vast distances between stars are minuscule compared to the distances between galaxies and superclusters. The universe, in essence, is a hierarchy of scales, each level expanding exponentially, and each layer more incomprehensible than the last. Extreme distances also redefine our understanding of motion and interaction in the universe. While galaxies within clusters interact gravitationally, galaxies across vast inter-supercluster voids are effectively isolated. Collisions between clusters or superclusters are rare and occur on timescales of billions of years. Yet even in these vast spaces, the expansion of the universe continues to drive structures apart, stretching the cosmic web and slowly increasing the separations between the largest cosmic structures. These distances remind us that the universe is dynamic, vast, and continually evolving, with a scale so large that conventional intuition fails entirely. Extreme distances emphasize the challenge of human exploration and observation. Sending probes or signals across interstellar distances is already daunting. Reaching other galaxies, let alone neighboring superclusters, is currently beyond technological possibility. Even light, the fastest entity in the universe, takes millions to billions of years to traverse these distances. This reinforces the humbling notion that while we can observe and model the universe, we remain confined to a tiny corner of it, separated from much of its structure by scales so immense that they challenge the very notion of reachability. Light is the universe's messenger, the primary tool by which we perceive and measure cosmic structures. It is the medium through which information about stars, galaxies, nebulae, and the large-scale structure reaches us. Yet, as vital as light is, it also imposes fundamental limits on our understanding. Because light travels at a finite speed, approximately 209,792 kilometers per second, or roughly 186,282 miles per second, it constrains what we can see, how far we can observe, and how accurately we can measure distant objects. This limitation shapes not only astronomy, but the very scale at which we perceive the universe, embedding temporal and spatial constraints into our knowledge. The finite speed of light means that when we observe distant objects, we are always seeing them as they were in the past. Light from the sun, for example, takes about 8 minutes and 20 seconds to reach Earth. The image we perceive is not the sun's current state, but a snapshot from over 8 minutes ago. Stretch this concept to the nearest star outside our solar system, Proxima Centauri, and we see it as it appeared 4.24 years ago. Expand it further to galaxies millions or billions of light years away, and we are observing events that occurred long before Earth itself formed. Light, therefore, is both a tool and a time machine, carrying information across vast distances, but delivering it delayed by the expanse of space. The universe we see is always a view into the past, never the present, and this intrinsic limitation shapes our understanding of cosmic events and structures. Beyond temporal delays, the speed of light sets a hard boundary on causality and observability. Nothing can travel faster than light through space, meaning that events separated by distances greater than the light travel time remain causally disconnected. Galaxies receding faster than the rate at which light can traverse the expanding space between them are effectively beyond our observational reach. This establishes the cosmic horizon, the ultimate limit of the observable universe, beyond which we cannot obtain information, no matter how advanced our technology becomes. Light speed, therefore, defines the very boundary of what is knowable and places intrinsic constraints on the scale of human observation. Light also governs how we measure distances in the universe. Astronomers rely on various methods: parallax for nearby stars, standard candles like Cepheid variables, and type Ia supernovae for intermediate distances, and redshift measurements for the most remote galaxies. All of these techniques depend on the behavior of light, from its apparent brightness to its wavelength, and each is affected by the finite speed at which it travels. Redshift, in particular, is a direct consequence of light moving through expanding space. As space stretches, so does the wavelength of light, shifting it toward the red end of the spectrum. By analyzing this shift, astronomers can infer how fast distant galaxies are receding and estimate their distance from Earth. Without light and its predictable properties, it would be impossible to map the universe or quantify its immense scales. However, relying on light also introduces challenges. Dust, gas, and intervening matter can absorb, scatter, or distort light, making distant objects dimmer or harder to observe. Cosmic expansion further complicates matters by stretching light across vast distances, sometimes shifting it out of the visible spectrum into infrared or radio wavelengths. Detecting and interpreting such faint, stretched light requires increasingly sensitive instruments and creative observational strategies. Observatories like the Hubble Space Telescope, the James Webb Space Telescope, and radio arrays such as ALMA allow scientists to capture light across the electromagnetic spectrum, revealing phenomena that would otherwise remain invisible. Even so, the speed of light ensures that our view of the universe is inherently incomplete, constrained to what photons have managed to reach us. The limitations imposed by light's finite speed also have philosophical and practical implications. The universe, in a sense, is only partially revealed to us. Galaxies currently beyond the cosmic horizon may exist, yet no light from them can reach us now or in the future if cosmic expansion accelerates. Even within the observable universe, we are always seeing a version of reality that is delayed, and this delay grows with distance. The farther we look, the deeper we peer into the past, and the more removed the observed events are from the universe as it exists today. Light provides knowledge, but it also imposes a fundamental boundary, ensuring that some aspects of cosmic reality remain forever beyond reach. Furthermore, the role of light emphasizes the interconnectedness of distance and time. Observing light from distant stars and galaxies is not merely an exercise in measuring space. It is a journey through epochs of cosmic history. The images captured by telescopes are frozen records of the past, offering insights into stellar evolution, galaxy formation, and the growth of cosmic structures. Light is, therefore, both a messenger and a historian, encoding information about processes that may have occurred billions of years ago. This dual role enhances its importance in cosmology, but underscores the limitations inherent in our understanding. We cannot interact with or alter the events we observe. We can only study the light they emitted. The speed of light also imposes constraints on how we conceptualize motion and expansion. Galaxies in distant regions recede due to cosmic expansion, sometimes at apparent velocities exceeding the speed of light relative to us. While this does not violate the laws of physics, since it is space itself expanding, the photons emitted by these galaxies may never reach our detectors, placing entire regions of the universe permanently out of reach. The finite speed of light thus interacts with the dynamics of the cosmos, defining which structures we can detect, study, and understand. It makes the universe both knowable and unknowable, vast yet limited by the very nature of the signals that convey information across its expanse. In summary, light is the universe's ultimate informant, delivering knowledge across unimaginable distances while simultaneously enforcing hard limits on what can be known. It provides a time-delayed view of distant objects, a means of measuring distance and motion, and a window into the cosmic past. Yet it also defines the boundaries of observation, restricts causality, and ensures that some regions of the universe will remain forever hidden. The speed of light is not merely a physical constant. It is a fundamental feature that shapes our perception of scale, structure, and history. Without light, the universe would be entirely unknowable. With light, we see a universe of staggering vastness, intricate structure, and profound temporal depth, even as its full scope remains tantalizingly beyond our reach. Measuring cosmic distances is one of the most fundamental challenges in astronomy, yet it is essential for understanding the structure, scale, and history of the universe. Because direct physical measurement is impossible across such vast expanses, astronomers have developed ingenious methods that rely on light, motion, and the intrinsic properties of celestial objects. These methods form a cosmic distance ladder, where each rung extends our reach progressively farther into space, allowing us to chart distances from nearby stars to the farthest observable galaxies. The most direct and reliable method for nearby stars is parallax. Parallax is the apparent shift in the position of a star against the background of more distant stars as Earth orbits the Sun. By observing a star at different points in Earth's orbit, 6 months apart, astronomers can measure the tiny angular displacement and, using basic trigonometry, calculate its distance. This method works well for stars up to a few thousand light-years away, and it provides a foundation for calibrating more indirect techniques. Modern missions like Gaia have measured the positions and distances of over 1 billion stars with unprecedented precision, greatly refining our understanding of the Milky Way's structure and local stellar neighborhoods. Beyond the reach of parallax, astronomers rely on standard candles, objects with known intrinsic brightness. By comparing their true luminosity to how bright they appear from Earth, we can determine their distance using the inverse square law of light. Cepheid variable stars, which pulsate at regular intervals, are classic examples of standard candles. Their pulsation period correlates directly with luminosity, allowing precise distance estimates. Type Io supernovae, catastrophic explosions of white dwarf stars, serve as another standard candle on a larger scale, observable in distant galaxies. Because these supernovae exhibit consistent peak luminosities, they enable measurement of distances up to billions of light-years, providing critical data for mapping the expansion of the universe. Redshift is a complementary method, essential for measuring the distances of the most remote galaxies. As the universe expands, space stretches the wavelength of light traveling through it, shifting it toward the red end of the spectrum. The amount of redshift is proportional to the galaxy's recessional velocity and, by extension, its distance from us. Using Hubble's law, astronomers can translate redshift into approximate distances, revealing the structure of the large-scale universe and the rate of cosmic expansion. Redshift measurements have been critical for discovering that the universe is not only expanding, but doing so at an accelerating rate, leading to the inference of dark energy. These methods are interconnected, forming a ladder that extends from nearby stars to the edge of the observable universe. Parallax calibrates standard candles, which in turn anchor redshift distance relationships. Together, they allow astronomers to measure distances across the vast hierarchy of the cosmos, from individual stars to galaxies, clusters, and superclusters. Without these techniques, the immense scale of the universe would remain speculative, and the intricate patterns of cosmic structure would be invisible. Measuring cosmic distances is not just about numbers. It is about understanding the very architecture of reality. Distances define the relationships between stars, the separation of galaxies, and the scale of superclusters. They also underpin calculations of the universe's age, the rate of expansion, and the mapping of the cosmic web. The methods may rely on subtle shifts in light or the predictable behavior of stars, yet they unlock knowledge about regions so vast that human imagination struggles to comprehend them. When contemplating the scale of the universe, numbers quickly become so vast that they defy ordinary human comprehension. Even the concept of billions of galaxies and trillions of stars is almost meaningless in our everyday experience. We lack the intuitive sense to grasp quantities so enormous. To bring some perspective to these mind-boggling numbers, astronomers and educators often use analogies, comparisons, and conceptual scaling, but even these pale in the face of the true immensity of cosmic scales. Yet understanding these numbers is essential because they highlight not only the universe's size, but the incredible diversity and complexity contained within it, and the infinitesimal fraction that humanity occupies in the grand scheme of existence. Consider the Milky Way, our home galaxy. It contains approximately 100 to 400 billion stars, each potentially orbited by planetary systems. To imagine a single billion, picture counting one number per second. Reaching 1 billion would take over 30 years. Now imagine doing that hundreds of times to account for the number of stars in the Milky Way alone. Even this does not capture the full picture. The Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. These galaxies range from massive ellipticals containing trillions of stars to tiny dwarf galaxies with only a few million. Multiplying these numbers, we find that the total number of stars in the observable universe is at least on the order of 10^24 to 10^25, an almost inconceivable figure. To put it in perspective, this is more than all the grains of sand on every beach and desert on Earth combined by many orders of magnitude. Using analogies helps, but even they fall short. Imagine assigning a unique grain of sand to represent each star in the Milky Way. Your driveway, your local beach, your country's deserts combined would not come close to representing them. Stretch this analogy to all the galaxies in the observable universe, and the entire Earth, all its beaches, deserts and oceans, would not provide enough sand. The numbers simply escape the human mind, and this is still only the observable universe, the regions of space from which light has reached us. Beyond that, there may be far more galaxies and stars, potentially an infinite number if the universe itself is infinite. Numbers on this scale are not just abstract, they have profound implications. Each star is a potential solar system, and each galaxy a possible cradle for countless worlds. If even a tiny fraction of stars host planets capable of supporting life, the potential number of habitable worlds across the cosmos is staggering. The famous Drake equation attempts to estimate the number of technologically advanced civilizations, but even a conservative estimate multiplies the enormous number of stars, planetary systems, and the probability of life arising into figures that strain credulity. The sheer numerical scale implies that the universe may be teeming with possibilities, even if the vast majority remain forever out of reach. To illustrate further, consider the distance analogy. If each star were represented by a millimeter in a vast cosmic model, the Milky Way alone would stretch hundreds of kilometers in this scale model. Now imagine representing all galaxies in the observable universe at the same scale. The model would extend beyond continents and oceans, spanning the entire planet and far beyond. Even this conceptual model, enormous as it would be, captures only the light we can see. Beyond our observational limits, the universe could contain regions that dwarf our imagination entirely. These analogies attempt to bridge the gap between human perception and cosmic reality, but they ultimately highlight how inadequately our minds are equipped to process such scale. Another way to grasp unimaginable numbers is through time. If each star in the universe were a second, counting every star would take far longer than the current age of the universe. Even counting at the speed of 1 million stars per second, it would take billions of years to reach them all. This illustrates that stars are not just numerous. They exist in quantities that transcend human timescales, stretching across the lifespan of the cosmos itself. Galaxies, clusters, and superclusters add additional layers, creating structures that grow exponentially in number and size. When we consider cosmic structures in this context, the numbers are not merely large, they are almost beyond any practical method of comprehension. The concept of scale also applies to distances and cosmic motion. Within the Milky Way, stars are separated by light years, and even neighboring stars are separated by vast voids. Multiply this by billions of stars and trillions across the universe, and the separation between objects grows correspondingly immense. Each galaxy is a minuscule island in a vast sea of cosmic voids. Clusters and superclusters are separated by tens, hundreds, or even thousands of millions of light years, further emphasizing the hierarchy of scale. The numbers of stars, galaxies, and structures are incomprehensible, but so too are the distances between them, creating a multi-dimensional vastness that is both numerical and spatial. The mind-bending scale of these numbers also has a profound effect on how we understand probability and existence. Even the most statistically improbable events become inevitable when considered across trillions of stars and billions of galaxies. The formation of planetary systems, the emergence of life, or the occurrence of rare astrophysical phenomena is almost guaranteed somewhere in the universe, simply due to the sheer quantity of opportunities. The larger the numbers, the more extraordinary events become commonplace somewhere else, expanding our imagination to consider possibilities far beyond Earth and our solar system. Yet, despite the enormity, there is still a sense of unity and interconnectedness. Stars form galaxies, galaxies form clusters, clusters form superclusters, and superclusters weave into the cosmic web. These structures, immense though they are, exist as part of a coherent cosmic architecture, shaped by gravity, dark matter, and the expansion of space. The numbers involved are almost meaningless in isolation, but they gain context and significance when understood as part of this grand cosmic network. The universe is a hierarchy of unimaginable numbers, each layer contributing to the whole in ways both intricate and elegant, from the smallest star to the largest supercluster filaments. Even when we attempt to visualize such numbers, analogies like grains of sand, seconds, or scaled distances serve only as conceptual bridges. They cannot truly capture the immensity of 10^24 or 10^25 stars, nor the countless possibilities contained within billions of galaxies. Our brains are simply not wired to process such scales intuitively. We must rely on mathematics, models, and abstract reasoning to comprehend the full magnitude. In doing so, we begin to understand that the universe is not just vast in space, it is vast in quantity, variety, and potential, encompassing numbers that stretch the boundaries of imagination itself. This recognition of unimaginable numbers also reframes our perspective of humanity's place in the cosmos. Earth, the Sun, and even the Milky Way occupy an infinitesimal fraction of the total observable universe. Our entire solar system, with all its planets, moons, and asteroids, is a speck among trillions of stars, dwarfed by billions of galaxies and the vast voids between them. This humbling realization does not diminish our significance, but rather situates us within a cosmic narrative that is far grander and more intricate than we can perceive directly. The scale of numbers invites both awe and curiosity, urging exploration, study, and philosophical reflection. These staggering figures emphasize the limits of human perception and the power of imagination. While the universe is filled with quantities that defy comprehension, we can use mathematics, observation, and analogy to gain a sense of scale and structure. Trillions of stars, billions of galaxies, and immense cosmic filaments remind us that reality is far larger and more intricate than our immediate experience suggests. By engaging with these numbers, we glimpse the immensity, complexity, and richness of the cosmos, a universe so vast that even with all our knowledge, we have only begun to scratch the surface of understanding its true scale. Our understanding of the universe is limited not just by its immense scale and the speed of light, but also by the capabilities of our observational tools. Throughout history, technological advances in telescopes and detection instruments have transformed humanity's view of the cosmos, revealing structures, phenomena, and distances previously unimaginable. From Galileo's first crude telescope to the sophisticated instruments orbiting Earth and stationed across the globe today, each leap in technology has extended the reach of our knowledge, allowing us to see farther, in greater detail, and across more of the electromagnetic spectrum. Today, we stand at a similar threshold, with new generations of telescopes poised to expand the observable universe and refine our understanding of its immense scale. The James Webb Space Telescope, launched to replace and enhance the discoveries of Hubble, represents one of the most advanced tools humanity has ever deployed, With its 6.5-meter primary mirror and state-of-the-art infrared sensors, Webb is capable of observing the faintest light emitted by the earliest galaxies, formed just a few 100 million years after the Big Bang. Infrared capability is crucial because the expansion of the universe stretches visible light from extremely distant objects into longer infrared wavelengths. Webb allows astronomers to peer deeper into space and further back in time than ever before, offering unprecedented insights into the formation of the first stars, the assembly of galaxies, and the evolution of cosmic structures. By observing these ancient objects, we are effectively extending the cosmic horizon, pushing the boundaries of what we can see and measure. Ground-based observatories have also advanced dramatically. Large telescopes like the Extremely Large Telescope, ELT, in Chile, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are engineered to collect more light than any previous instruments, dramatically improving sensitivity and resolution. These massive telescopes employ adaptive optics systems that correct for atmospheric distortion, allowing them to produce images rivaling those captured by space-based observatories. With these tools, astronomers can study galaxies at billions of light-years distance, examine the structure of distant superclusters, and investigate the dark matter and dark energy shaping cosmic expansion. The advent of multi-wavelength astronomy has further revolutionized observational capabilities. Different wavelengths of light, radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray, reveal distinct physical processes occurring in the universe. For example, radio telescopes like the Square Kilometre Array, SKA, map the distribution of hydrogen gas, the raw material for star formation, across vast distances. X-ray telescopes like Chandra and NuSTAR reveal the behavior of high-energy phenomena such as black holes and supernovae, while gamma-ray observatories detect the most energetic events in the cosmos. By combining observations across the spectrum, astronomers can construct a more complete picture of the universe's structure, composition, and evolution, even in regions billions of light-years away. New observational methods are also expanding our reach beyond traditional electromagnetic signals. Gravitational wave detectors such as LIGO and Virgo have opened an entirely new window on the universe. Gravitational waves, ripples in the fabric of space-time generated by cataclysmic events like colliding black holes or neutron stars, carry information from regions and events that may be invisible to traditional telescopes. By detecting these waves, astronomers can probe extreme cosmic environments, measure distances with remarkable accuracy, and gain insights into the universe's expansion and structure that were previously inaccessible. Moreover, technological advancements in data processing and artificial intelligence are allowing scientists to analyze unprecedented volumes of cosmic data. Modern surveys generate petabytes of information, far more than a human could process manually. AI algorithms can identify patterns, classify galaxies, detect transient events, and even predict the locations of previously unseen phenomena. These tools maximize the utility of the observational infrastructure, helping astronomers extract knowledge from regions of space that remain faint, distant, and challenging to study. Future missions promise to push the boundaries even further. Proposed telescopes like the Nancy Grace Roman Space Telescope aim to survey large portions of the sky with high resolution, searching for dark energy, exoplanets, and distant galaxies. Missions like the Laser Interferometer Space Antenna, LISA, will extend gravitational wave detection into the low-frequency regime, observing mergers of supermassive black holes across the universe. Combined with next-generation ground-based telescopes and radio arrays, these instruments will allow us to probe structures at previously unimaginable distances and even detect phenomena that occur in the earliest epochs of cosmic history. The expansion of observational capability has profound implications for understanding cosmic scale. As our instruments improve, the boundaries of the observable universe will expand, revealing more galaxies, clusters, and filaments. Each new discovery adds to the tally of stars, the mapping of cosmic structures, and our knowledge of extreme distances. With these tools, astronomers can refine models of galaxy formation, measure the distribution of dark matter, and study the processes that govern the evolution of superclusters and voids. Every increase in observational sensitivity opens a window to regions of space that, just decades ago, were entirely invisible. Technological progress also informs theoretical models. Observations from powerful telescopes help test predictions of cosmic inflation, dark energy, and the multiverse hypothesis. Detecting the faint light from the earliest stars or the subtle distribution of galaxies across billions of light years allows theorists to constrain parameters, validate simulations, and refine our understanding of the universe's expansion and evolution. In this sense, future observations are not only about seeing farther, they are about deepening our comprehension of how the universe works, from the smallest structures to the largest cosmic web. Additionally, the synergy between observational technology and international collaboration multiplies the potential impact of each mission. Global networks of telescopes, observatories, and detectors operate in concert, providing continuous coverage, complementary wavelengths, and cross-verification of discoveries. Large surveys map the sky systematically, revealing structures that individual telescopes might miss, while space-based observatories eliminate the distortions and absorption caused by Earth's atmosphere. This collaboration enhances our capacity to chart the cosmos with unprecedented detail, extending our knowledge both in breadth and depth. In essence, future observations represent a bridge to the farthest reaches of the universe, allowing humanity to peer deeper, earlier, and more precisely than ever before. They promise to extend the observable horizon, detect the faintest structures, and explore phenomena that were previously speculative or entirely invisible. Through the combination of larger telescopes, multi-wavelength observation, gravitational wave detection, advanced data processing, and international collaboration, our understanding of cosmic scale will continue to grow, revealing a universe more vast, dynamic, and complex than our current imagination can encompass. The universe is not a static stage on which cosmic objects merely exist. It is a dynamic, ever-changing expanse in which everything is in motion. From the rotation of planets to the drift of galaxies across intergalactic space, motion is a fundamental property of the cosmos, shaping its structure, evolution, and the relationships between celestial objects. Understanding this motion is essential for grasping the true scale of the universe, because the distances and positions we observe are constantly shifting, and the expansion of space itself accelerates the separation between galaxies, adding an extra layer of complexity to the already vast cosmic landscape. At the most local level, planets orbit stars, and stars orbit the centers of galaxies. The Earth, for example, travels around the Sun at an average speed of roughly 30 kilometers per second, completing a full orbit every 365.25 days. The Sun itself is moving around the Milky Way's center at about 220 kilometers per second, taking approximately 250 million years to complete a single orbit. Within the galaxy, stars move in orbits influenced by gravity, interacting through gravitational tugs, occasional collisions, and the subtle effects of dark matter. While these motions are minor compared to cosmic scales, they illustrate that even seemingly stable structures are constantly in flux. Galaxies, too, are in motion. Within galaxy clusters, individual galaxies orbit one another, drawn together by mutual gravitational attraction. Interactions, collisions, and mergers between galaxies are common over billions of years, dramatically reshaping their structures. When galaxies collide, stars rarely collide directly because of the immense distances between them. But the gravitational forces rearrange orbits, trigger bursts of star formation, and often create spectacular tidal tails and streams of stars. These motions on cluster scales reveal that galaxies are not isolated entities. They exist in dynamic networks shaped by gravity, interactions, and cosmic history. Beyond clusters, the motion of galaxies is dominated by the expansion of the universe itself. Ever since the Big Bang, space has been stretching, causing galaxies to drift apart from one another. This expansion is not the movement of galaxies through space, but rather the expansion of space between them, like dots on the surface of a balloon inflating over time. The farther apart galaxies are, the faster they appear to recede from one another, a relationship quantified by Hubble's law. For nearby galaxies, this recession is slow enough to measure in kilometers per second, but for galaxies billions of light years away, the apparent velocity can approach or even exceed the speed of light due to the expansion of space itself. This cosmic motion underscores that the universe is not static. It is a dynamic and accelerating entity, with distances continuously increasing on scales beyond galaxy clusters. The acceleration of cosmic expansion adds another layer of complexity. Observations of distant supernovae in the late 1990s revealed that not only is the universe expanding, but the rate of expansion is increasing over time. This surprising discovery led to the concept of dark energy, an enigmatic force that counteracts gravity on the largest scales and drives galaxies farther apart at an accelerating pace. As a result, regions of the universe that are currently observable may eventually recede beyond the cosmic horizon, disappearing from view entirely. This acceleration implies that the universe is not merely vast, it is actively stretching in a way that continually increases its scale and reshapes the observable landscape. On even larger scales, galaxy clusters and superclusters are part of a cosmic web in motion. Filaments of matter, stretching across hundreds of millions of light years, act as gravitational highways along which galaxies move. Cosmic voids, regions of lower density, expand as matter flows toward denser filaments and nodes, gradually reshaping the large-scale structure of the universe. These motions are slow on human timescales, but over billions of years, they significantly alter the arrangement of galaxies and the shape of the cosmic web. In this sense, the universe is alive with motion at all scales, from the spin of planets to the drift of entire superclusters. Even light itself is affected by this motion. The expansion of the universe stretches the wavelength of photons traveling through space, a phenomenon known as redshift. Light from distant galaxies is shifted toward longer wavelengths, which provides astronomers with a direct measure of cosmic expansion. The faster a galaxy recedes due to expansion, the greater the redshift of its light. By studying redshifts across millions of galaxies, astronomers can map the motion of cosmic structures, determine the rate of universal expansion, and infer the influence of dark energy. Light, therefore, not only informs us about distant objects, but also encodes the history of their motion and the dynamics of space itself. The motion of the universe has practical implications for measurement and observation. When we observe distant objects, we see them not just across vast distances, but also at different velocities and states of motion. Galaxies moving toward or away from us appear blue-shifted or red-shifted, and their relative velocities must be accounted for in distance calculations. The expansion of space itself means that distances are not static. The distance light has traveled may differ from the current separation between objects. Astronomers must carefully account for these dynamic factors when constructing models of the universe's structure, evolution, and ultimate fate. The universe's motion also highlights the dynamic interplay between gravity and expansion. On local scales, gravity dominates. Galaxies within clusters remain bound despite the overall expansion of space. On larger scales, however, dark energy overwhelms gravitational attraction, causing clusters and superclusters to drift apart. This duality explains why some structures remain coherent while others are stretched toward isolation, and it underscores that the universe's scale is not fixed but continuously evolving. Motion, therefore, is not just a property of individual objects. It is an organizing principle that shapes the cosmos, determining which structures remain bound and which are ultimately carried away by expansion. Ultimately, the universe in motion transforms our understanding of scale. Distances are not absolute. They change over time as galaxies recede and space expands. Structures that seem stationary are part of a vast cosmic dance that unfolds over billions of years. The dynamic nature of the universe magnifies the sense of scale we have already developed, showing that even if we could travel across interstellar or intergalactic distances, the target itself might be moving away, making the journey infinitely more complex. Motion, acceleration, and cosmic expansion turn the universe from a static tableau into a living, evolving system where size, distance, and position are all relative to time and perspective. As we step back and take in the enormity of the universe, from the trillions of stars in our own galaxy to the billions of galaxies woven into clusters and the vast cosmic web stretching beyond our view, we confront a scale that dwarfs everything familiar. Earth, our home, is an infinitesimal speck, spinning around a single star in one small galaxy among countless others. Yet within this immensity lies the remarkable fact that we, as observers, can comprehend even a fraction of it. Our telescopes, our measurements, and our curiosity allow us to glimpse the past, map the cosmic web, and imagine regions far beyond what light has revealed. This perspective is both humbling and inspiring. It reminds us that while the universe is vast beyond measure, our capacity to explore, to question, and to understand gives us a unique place within it, a tiny point of consciousness in an ocean of cosmic scale, yet capable of marveling at its infinite beauty. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.